Thank you very much for the introduction. I'll just go ahead and get started with my presentation. I think I'm supposed to be at 4:30, but it's a bit earlier now. It's fine. So hello, everyone. My name is Fangzhou. I'm currently actually a postdoc at the Massachusetts Institute of Technology, working in the mechatronics research lab. So today I'll be talking about AFM active cantilever probes development for the new capabilities. So we'll first provide a general background introduction of the AFM for those who are not familiar, and then focus on the development of the active cantilever probes used in this work. And then this is to use to realize imaging in chemically harsh opaque liquid environment with the primary focus of the application. And after that, we'll be going through the broader range of capabilities enabled with this specific active probe design. I will cover that. And in the end, a review on various more active probe designs using different physical principles will be covered in the end. Okay, let's get started with the background. So, atomic force microscope, I'll give a brief principle overview for those who are not familiar with this instrument. So it's a nanoscale topography imaging tool for surface characterization. In its basic form, it creates a 3D high topography image for sample surface with sub-nanometer resolution. The key components of an AFM would include the cantilever probe. Here we have a nano-positioning system. So here we have a coarse engagement system on the base and a high-resolution scanner at the top. And also there is an imaging control system designed centered around the cantilever as well as the nano-positioner. AFM scans the micro-cantilever over the sample to measure the various quantities, not only topography, but also other electrical or mechanical optical properties. The deflection of the cantilever will be regulated by this control system to avoid damaging, and either for the probe or for the sample. To conduct an AFM experiment, there are primarily 5 steps involved. So the first step is the sample preparation. It's to prepare the sample to be characterized and fabricate it and shape it to fit into the instrument, depending on the discipline. And the second thing is the equipment calibration. This step is usually needed to ensure good imaging performance and always usually completed by the vendors. And then we have this experimental setup, which depends on AFM principle. Either we need some laser alignment for the probe as well as the laser for beam deflection sensing. And we have this probe sample engagement, so that we need to bring this probe into contact with the sample. For the first step, we have the imaging and controller tuning, which is the AFM user that needs to adjust the parameters during imaging to ensure good tracking performance. For the last step, we have the AFM image post-processing. So this is to convert the collected data to process them and visualize them so that we can interpret the results. So depending on the state of the cantilever, there are actually several modes of operation. We are doing this on a very high-level categorization for 3 general modes. First would be saying it as contact, which is the probe and the tip. The probe tip and the sample remain in contact while the cantilever deflection is being regulated by the controller. And the second one is the dynamic modes, where the resonance mode of the cantilever is excited. Being a continuous system, it can either be the first mode, the second mode, or sometimes even multiple modes. That's why there are different sub-modes within this category. But nevertheless, in all of them, we have the resonance at one frequency being excited, and then the cantilever deflection characteristic is being regulated for the oscillation, either being the amplitude, the phase, or sometimes frequency. The third one is actually we call it the jumping modes. There are different names for this one, but in this case, the probe tip and the sample makes intermittent contact. And also the resonance of the cantilever is not excited. So this mode is suitable for quickly covering a larger imaging range because it does not have to ensure very good tracking for adjacent point of contact. You can jump from one point to the other, which has a large distance between each other, and then you can get the sample measured at those pixel locations. So now that we have a general understanding of the principle and operational basics, I will proceed to talk about the substantive development in this work. So we will primarily focus first on the cantilever probe, starting with the conventional, we call them passive AFM cantilever. Conventional AFM systems, they use this passive cantilever probe produced with nano-fabrication techniques. The probe is composed of a base support chip, which is this guy here. Probably industrial standard is this 3.4 by 0.3 by 1.6 millimeter for most chips. And then there is a micro cantilever beam. So this is being etched on the base support chip. So we have a cantilever. And at the very end of the cantilever, we have this tip. So we can also fabricate multiple cantilevers at the same time, just to save the cost of nano-fabrication, and also produce tip with different geometries depending on the application. Sometimes sharpened ones are needed, sometimes blunt ones are desired. So to contrast the active and the passive one, we want to say that passive ones has no embedded elements. As you can see here, these are just a built bulk silicon or sometimes silicon nitride material. For deflection measurement, the passive probes are usually using, for most of the AFM currently commercially available, use this so-called the optical beam deflection sensing. So basically in this case, we have a laser, and this focus at the back surface of the cantilever, and then it's reflected and being picked up by this quadrature photodiode, where the motion of this laser is amplified by the optical path, and then we can get to the tip deflection, usually on the sub-nanometer resolution. As you can see here, we will require a transparent path for the light to go through in this case. For most applications involving the resonance excitation for the dynamic modes, people use this piezoacoustic actuation for cantilever resonance. Basically, we put a piezo actuator at the base of the cantilever, either on the support chip or sometimes even far away from it. But once you have the structure being excited at the frequency, we will have this amplitude at the cantilever being amplified due to the large Q factor typically available on micro cantilevers. So these are the basic principles. But if you want to do some imaging, for example, in our case, in opaque liquid, then this optical beam thing will not work, basically because the laser requires transparent light path. So that essentially means we need a different driving principle to work in those specialized environments. So now we can take a look at the active probe principle and design, now that we know what the passive probe does. So for active probe, the one we use in this work, we'll take a look now. So this utilizes this embedded sensing and embedded actuation. So we have a piezoresistive Bimorph cantilever. As you can see here, we have 4 piezoresistors embedded at the base surface of the cantilever, where the internal stress is maximized whenever we have a cantilever probe deflection. So this is in a Wheatstone bridge configuration so that we can sense the deflection very accurately. So to drive the cantilever probe, we use something called electrical thermomechanical Bimorph actuation. Basically, you have 2 layers of material, which is silicon and silicon nitride, being heated by these aluminum wires, which is resistive electrical power converted to heating. So once we have the temperature difference, this microcantilever will be bent to one direction. So this allows embedded actuation and sensing without the need for external elements. For the sensing, it removes the need for the optical transparency. For actuation, it can actually allow you to control the static deflection. Rather than for the piezoacoustic, you can only excite resonance. You cannot really control this cantilever to bend to one direction. But of course, this is realized at the cost of the temperature sensitivity, basically because this probe will be sensitive to temperature variation. If you are trying to do this measurement in a different temperature, that will not work for this design. Okay, so with the change of the physical principle, the governing equations for the active probe is actually a bit more involved. This is a visualization for the signal path involving both active probe signal path for actuation in red, sensing in green, as well as the demodulation in blue. There are also models illustrating this entire AFM loop, but we will primarily be focusing our attention on the active probe part. So we understand these principles for interfacing with the cantilever. Well, first, let's look at the red part for this so-called half omega voltage drive. Basically, this is because for thermal heating, we will have a signal being squared, because for the power generation, we have the voltage squared divided by R as the resistive heating power. In that case, if you have a DC and an AC component, by trigonometry identity, you have 2 different omega components spaced at the first omega and 2 times the omega frequency. So if you want to drive the probe purely for 1 omega excitation, then we will actually be using the omega frequency half of the resonance, so that we set the DC component to 0, and then we'll be using primarily this 2 omega term, which is now equal to the resonance frequency to drive the probe. So the temperature change will be proportional to the heating, which results to in a tip deflection. We call them delta Z, as here in the orange color. So this is actually not very easy to analyze, but analytic solution does exist for simple, just two-layer system, which we can use this constant K. It's just a constant depending on geometry and the thermal conductivity and coefficient of expansion in the material. This T represents the temperature, which is the cantilever being heated to, and T naught is just the original temperature. And L is the length of the cantilever. So in this case, we have this delta Z directly proportional to this one, so that we can control the cantilever static deflection through resistive heating. We can also prove from basic mechanics that the cantilever force is related to its deflection ZL by this formula, as well as this tangential angle, the theta L, by this formula. So basically, they are linear relationship, which allows us to do the measurement in an easier way because the linear relationship in this purple F. In the end, we have this sensing part, which is this green thing here. We have this power output from the Wheatstone bridge with bridge supply U and piezoresistive coefficient PR and a bunch of geometric LWH constants, which we'll not go into details. This measurement accuracy is limited only by the piezoresistive noise, which is the Z noise term here. So in general, this kind of probe for our application, we can observe like between 20 to 100 kilohertz is the typical first resonance frequency, which we can use for like a tapping mode imaging. So just to produce this cantilever, we use nano-fabrication. Basically, here is a very high-level illustration on the left for the steps. So basically, silicon nitride Bimorph structures are first formed with deposition, and then the piezoresistors are formed by p-type doping of the silicon material. Aluminum heating wires are formed with photolithography, and the fabricated active probe is attached to an SD card-shaped printed circuit board with lead wires bonding for easy manual handling. This is shown on the right-hand side. You can see approximately this is around like over 1 inch for the length. Allows people to handle it manually pretty easily compared to normal cantilevers, which is just at the tip size here. People have to use tweezers for handling those cantilever, which might be difficult for novice users. So to enable the imaging in harsh opaque liquid, we resolved the principal level issue for optical transparency, but we now have elements that are active, that are on the cantilever. They need to be protected by coating material. So basically, the property of the cantilever should not be changed significantly so that the imaging capability can be maintained. With the delicate nature of these nano-fabricated cantilevers, we tried various material and found that the dip coating using something called the positive 20 photoresist offers a good balance between the performance for probe protection and imaging. So we can see the comparison image for the active probe front and back surface before and after coating here. With system identification, we also found that the coated probes have increased values for stiffness, mass, resonance frequency, and the thermal time constant. But still, the resonance peak that is reduced in Q factor is preserved. We can use that for tapping mode imaging without too much trouble. So this coated probe is used to capture the grating image in crude oil, which we'll show later. So to do that, we first need a custom AFM. So this is a custom AFM design using a multi-actuation scheme. The system can work with both passive probes, regular ones for optical beam deflection sensing, as well as the active one we just see here. And also it can do both high-speed local scan as well as a large range overview for 100 micron cubed. So we're not going into the details of the instrumentation since it's not the focus of this talk, but rather to see how this system is used for the active probe imaging of opaque liquid. Okay, so here are the illustration of AFM system taken from the publication for nanomaterials that illustrate assembly of the AFM system and the signal path. So basically, we need to develop a custom locking amplifier to do the 2 omega demodulation on FPGA. And then we also have a color-coded SEM image of the probe that we used. All right, so using the coated active probes, when we protected the embedded components, we can put that into the water, no problem for sure. And also we use that for imaging. So we use this AFM system for imaging opaque acid and also opaque crude oil to verify its capability. So the coated active probes have also previously been used for imaging of yeast cells in saline solution. And so this development has the potential for image applications in biology, chemistry, and refinery for studying samples in their native environments, which in many cases can be non-transparent. So this will be like the key of development we want to discuss in this case here. All right, now that we've seen one example application, we want to discuss a bit more about the broader applications of active cantilever probes for various other applications. So compared to passive cantilever probes, active probes have several benefits. First, the compact probe design allows easy probe scan configuration and embedded applications in confined space. So it reduces operational overhead for probe laser alignment and allows parallel probe design. So the embedded actuator can be also avoid structural resonance in like piezoacoustics case. And also a number of applications are enabled for the functionalized active cantilever probes. First, the design can be used for sensing such as like mass detection, chemical, biological, temperature, and calorimetry sensing. Second, the probe can be used in specialized environments, such as the harsh opaque liquid we just saw, and also in confined space, such as the AFM in SEM system. Also, it can even be used in outer space. Third, there are a number of modes, such as lateral force, parallel probe array, multi-eigen modes, electrical property mapping, scanning thermal probe, and coaxial scanning near-field optical microscopy that have been investigated with this probe in the past, either from a group or from our collaborators. But last but not least, the probe can also be used for nano-fabrication applications, such as scanning probe lithography, single ion implantation, nanojet printing, and also the in-situ observation tool for ion beam machining or deposition. So this is just a long list of them. We'll see some selected examples with figures, and then to get a vivid idea. So with the small probe footprint, we can use it to do the sensing of like variations in small mass. So for example, if the active cantilever probe is functionalized with specialized materials that can absorb certain particles, the added mass will cause a shift in the resonance peak that can be detected and used for sensing. The array of cantilever functionalized with different materials can be used as an electric nose to measure various particles. So this bimorph structure can also be used for actuation as well as for temperature variation sensing, because external temperature change can result in the deflection of the probe. In another examples, we have active probes for AFM in confined space. So with small footprint, the active probe can be easily fit into spaces where spaces are very limited. So this is like not possible with conventional optical beam deflection with bulky external components. With embedded sensors, the active probes can also be producing arrays. So this is showing like 4 parallel cantilever probes, active ones, imaging one sample simultaneously. So they are spaced for 125 micron. You can move over that range and then stitch 4 images together to get a large range overview of the sample in a fairly quick manner. So for active probe, new modes of operations, this is showing scanning near field coaxial optical microscopy. This is realized by putting an aperture at the tip by focused ion beam machining. So since active probe don't really require external optical sensing at the back of the surface of the probe, this will be quite helpful because it's not that complicated to get that probe aperture fabricated and used in this case. And also, if you put a temperature-sensitive filament attached to the cantilever, it can be used for thermal imaging. Last but not least, we have this active probe for nano-fabrications. So basically, it can be used for scanning probe lithography if we have a conductive wire connected to this probe tip. And also, it can be used for high spatial resolution, single ion implantation. Basically, you need to use aperture at the very tip of the probe so that whenever you image it using AFM to see where this is location I want to implant my ion, and then we can turn on the ion source to get that implantation done. It can also be used to filter those nano-jetting of particles rather than ions, as visualized in this slide. Okay, the last section that I want to give a brief review of active probe designs and also various sensing principles, not only involving active ones. For example, this is a summary slides that are available in the literature that we reviewed for various actuation and sensing principles that has been used for AFM application with the cantilever. So there is the physical principle, functions, signals, size and location, and the main limitation sort of like described in this table. The one we use is this color in red, the piezoresistive, as well as electrical thermal for actuation and sensing. And they are both embedded as labeled in blue here. But we have also more blue examples, and also the size and location can be different for non-embedded ones. Here are just some very high-level examples. This is the probe sensing using optical beam deflection. We've seen it before, so I'm not going into details. Basically, one thing to point out is like this thing can be done in 3D for alignment. So it can be sometimes complicated to do the alignment to get a very good signal-to-noise ratio if you're not an experienced user. The next principle is the so-called Astigmatic detection. Basically, people use the CD or DVD drive that uses Astigmatic principle to get the distance measured for the pits in the CD and DVD drive. It can also have a small linear region in the middle that people can be using that for the micro cantilever sensing in the AFM operation. Another optical-based method would be the interferometry. Basically, for the probe sensing, you shine a laser at the cantilever. This is called the interdigited cantilever. And once the one reference cantilever is held as stationary in the air and the other is interacting with the probe, you can get the interference pattern change so that we can measure the motion of the cantilever. For actuation, we have first the piezoacoustic one. We talked about it before, so we'll not be going into the details. But nevertheless, this is one way people mostly use. As you can see here, the commercial Bruker probe holder has a piezo far away from the cantilever location, which excites the entire structural resonance. We have probe actuation for optothermal, basically for heating and Bimorph using optical power. And also we have probe actuation for electromagnetic. Basically, this is just using magnetic field and magnetic particles, either external coil or internal on the cantilever for the actuation. In the end, we have this electrostatic probe actuation, which can be used for external probe actuation just for electrostatic forces. But all these are not active. What we want to focus our attention on is active probe examples. So this slide is a lot of text, but we want to go into the details about how they're actually used in real designs. Let's take a look at the active probes with the pictures. We have the optomechanical Bimorph sensing. So basically, Bimorph structure is similar as the one we mentioned before, but people use this optical Everson coupled optical microdisc causing frequency modulation in this probe for the measurement of deflection. We also have this Q+ sensor with Quartz tuning fork, the piezoelectric Quartz tuning fork available commercially, being attached with a sharp tip so that people can do the sensing and actuation, basically in the same setup without too much nano-fabrication. People have improved this design by something called an Akiyama probe, which is a micro cantilever being attached to the piezoelectric tuning fork. And that is used to get the measurement for this motion up and down with a softer cantilever so that we can have a larger motion of the probe oscillation. Another probe based on piezoelectric material would be to nano-fabricate all the piezoelectric material onto this micro cantilever. This is more complex to fabricate, but offers the benefit of like a different probe tip geometry, and also this probe is significantly softer than the tuning fork ones. In the end, people have this active probe for MEMS scanner, which has been already commercialized with something called an N-gauge AFM. In addition to this cantilever being self-sensing and self-actuated, electrostatic MEMS scanner and electrothermal sensors for feedback has been embedded in this scanner design. So basically, it operates only in air for now, but it can be quite helpful for system on chip because the footprint is quite compact. As you can see here, basically, this is an entire AFM system. There's no need for external bulk scanners. The only thing that's needed would be this engagement system to bring the probe and the sample into contact. All right, with that, I want to conclude this talk. So basically, we discussed the active cantilever, which is a promising technology with a number of benefits. So we offer example application for the harsh opaque liquid imaging using coated active probe. And the ability to modify cantilever probes enables a number of new possibilities for characterization and nano-fabrication. The broader aspects of AFM development will include a lot of them, like the positioner, cantilever, controller, driver, optics vision, software integration. So basically, due to the time limit, we will not be discussing all that in detail, but we do get a general overview about the cantilever aspect in detail. So for the future work, we'll try to extend to new imaging capabilities and modalities for various applications. All right, with that, I would like to thank my colleagues and advisors, basically, and thank you very much for your attention.